A lot of people find solubility to be a tricky thing to predict. And usually the reason for that is that they focused on memorizing rules and thought that the exceptions were the least important part. Really, both of these are going to be really critically important. And I like to use a light switch as an analogy. Now, normally you'll have your light switch turned off because you're asleep or you're not at home. But when you want to go cook dinner and you're going to be using some sharp knives, you want the ability to turn it on. Same kind of thing as what we're talking about with the solubility rules. It's great when it does one thing most of the time, but you can toggle the switch to make it do something different. Now let me show you why. So all of these are typically going to be soluble. It's great to have these ones that are always soluble because it's a way that you can deliver whatever the other ion would be. In these cases, it's a great way to deliver an anion, a negative charge. In these cases, it's a great way to deliver a cation, a positive charge, and make sure that it will be soluble at the beginning of the reaction, and that they can then react with things to give a different product with the other thing you mixed it with. Now, example of that would be if you have chloride, bromide, or iodide, those are always going to be soluble. So if I had sodium chloride, table salt, that's going to be soluble. Why is that useful? What if you're trying to precipitate some silver? Silver will always precipitate with the chloride ion. So I can put sodium chloride into water and it will be soluble. If the chloride ion is around silver ion, it will force it to precipitate as silver chloride. Same with this ion. Now make sure you remember this the right way. It's Hg2, 2+. In other words, it's two atoms of mercury that are just always associated with each other. It's kind of a covalent bond. It's a little funky. I'm not going to go that far into that one. Just remember that it's going to have the +2 charge and two atoms that are inside of it. That makes the oxidation number of each one +1 if you're trying to connect the dots back to oxidation number. Now, lead 2+, all of these are going to give insoluble compounds. Same thing down here with the sulfate ion. If sulfite's paired up with any of these ions, it's also going to be insoluble. Now, that's going to be a really useful trick. You can take something that's normally soluble and precipitate it with something else. We have the flip side of that too, hydroxide. Now we know that hydroxide can be soluble because if we use sodium hydroxide, that's one of our strong bases. We use that in the lab all the time. But hydroxide ions aren't nearly always insoluble unless paired up with group 1. Notice that these group 1 and ammonium ions are also ones we said were always soluble. So these are going to be soluble with hydroxide or with sulfide. Anything else it precipitates. So if you had calcium, you expect to be able to get calcium carbonate as a solid. That's chalk. Now, just to highlight why these exceptions matter so much. So calcium chloride will precipitate. Calcium hydroxide rather. If you're having calcium hydroxide, you got to get the hydroxide ion there. You've got to get the calcium ion there somehow. So you'll need to pair up something with calcium that is soluble. We don't have anything showing right there, but calcium sulfate might be an example of that. Nope. Sulfate with calcium is insoluble. So see how you have to start thinking through tricks and putting them together? So you have to say, okay, well, calcium wouldn't do it. With sulfate, maybe I can do calcium acetate. I look at the acetate ion. No important exceptions. Calcium acetate would be something I could deliver. So it'd be Ca, then the C2H3O2 grouping would be 2 times. It's a -1 charge. You'll need 2 of those ions. You can see you can start chaining these things together. Now, if you're using a different table, though, I want to point this out. You'll find a lot of similarities between any solubility table. This is the one we're going to be using for our course. But most of them don't specify the distinction of slightly soluble. That's an important distinction that's going to matter a lot when we get to chemistry too, because now we can actually start having some things that are controlled when we do an equilibrium calculation. Now, all of these rules that we have here are the crude rules. Why are they crude? Simply put, it acts like everything's either an on, off, or a maybe. That's not very refined. In chemistry 2, what we'll do is we'll get as far as equilibrium. And when you do a calculation using equilibrium, you'll actually be able to decide how much is dissolved under various conditions. And that's where you get a lot more refinement. That's when you start saying that calcium carbonate does dissolve a little bit in water. How much is a little bit? You stop using the phrase slightly and actually do a calculation. Last one is going to be the carbonate ion and the phosphate ion. They're going to pair up with these ones to stay soluble, but with everything else they're going to be insoluble. So calcium carbonate is a good example of something that's insoluble. Calcium phosphate. But if you wanted to have phosphate ion, because you're making, let's say, for people who are doing this in biology, a buffer, well, you might pair it up so you're using potassium phosphate. Or you might stick some hydrogens on there so you have phosphoric acid. That's the other one I want to point out. We're not bringing up hydrogen in this table, but if you're looking at it like that, this is group 1, and group 1, and hydrogen is in group 1. So most of the group 1 has no exception. The ammonium ion typically has no exception. You can start to see that there's some things you can pull out of this that work pretty easily.